You see chemical reactions all the time, right? But have you ever stopped to think about what's actually going on down at the molecular level? Well, it's not chaos. It's more like a strict dance with a very clear set of rules. And in this explainer, we're going to pull back the curtain and look at that secret rule book. So let's start with the big question. What actually needs to happen for two molecules to successfully react? I mean, it's not just about mixing two things together and hoping for the best. There's a really precise physical process that governs everything from why bread rises to how a battery works. And believe it or not, it all boils down to just three fundamental molecular rules. Think of it like a three-point checklist. If a collision between molecules can check all three of these boxes, bam, you get a reaction. If not, well, nothing happens. This is the whole idea behind something called collision theory. All right, so let's dive into these rules. It all starts with the three keys to collide. This is the foundation of collision theory, and it spells out the absolute, non-negotiable requirements for pretty much any reaction to happen. Here they are, the big three. First, and this one's kind of obvious, the molecules must collide. They have to physically bump into each other. No contact, no reaction. Easy enough. Second, they have to collide with the right orientation. Imagine two puzzle pieces. They only fit together one specific way. While molecules are the same, the reactive parts have to be the parts that actually hit each other. And third, the collision needs to have sufficient energy. It has to be powerful enough to overcome what we call the activation energy barrier. Think of it like an energy hill they have to get over. And here's the kicker. This isn't a 2 out of 3 ain't bad situation. All three conditions are mandatory. If you miss even one, say they have enough energy but the wrong orientation, the molecules just bounce off each other like billiard balls. No reaction. It is an all-or-nothing deal. Okay, so if those are the rules of the game, how can we influence them? Maybe speed things up a bit? Well, this brings us to a key variable, heat. Let's take a look at why adding heat to a system is like hitting the fast-forward button for a reaction. So turning up the heat gives you a powerful 2-for-1 benefit. First, when things get hotter, molecules start zipping around like crazy. Faster movement means they just plain run into each other way more often. That's a greater frequency of collisions. But that's not all. The collisions aren't just more frequent, they're also way more powerful. A bigger chunk of the molecules now have enough energy to actually make it over that activation hill we talked about. Yeah, it's a real double win for the reaction rate. One of our sources puts it perfectly. You get a greater collision frequency and a greater percentage of the molecules having enough energy. So you have more chances to react, and more of those chances are actually successful. Boom. All right, so that's the big idea, the theory behind it all. But science, we love to turn concepts into an equation. So let's meet the formula that puts all of this together, the Arrhenius equation. Before I throw a bunch of letters at you, let's just talk about what this equation does. Its whole job is to be the mathematical bridge connecting how fast a reaction goes, what we call the rate constant, K, to its activation energy and the temperature. And there it is. K equals A times E to the power of negative EA over RT. Now, I know, it looks a little intense, but trust me, every single piece of this puzzle maps directly back to those simple collision rules we just went over. Let's break it down real quick. K is our reaction speed. E is that energy hill they have to climb. T is temperature. The two new guys on the block are A, the Arrhenius constant, and R, the universal gas constant. We're going to zero in on what A and that whole exponential part really mean. Let's start with that A factor. This is sometimes called the pre-exponential factor, and it's basically the math version of rule number 2. It represents the fraction of collisions that have the correct orientation to lead to a reaction. And the second piece, that whole exponential term, that's rule number 3. It represents the fraction of collisions that hit with sufficient energy to actually make it over that activation barrier. So you see, the equation is just saying reaction speed equals the fraction with the right orientation times the fraction with enough energy. It's literally just collision theory dressed up in a math equation. So that's what it is, but how do scientists actually use it? Because this isn't just something for an exam. This is a seriously powerful tool for chemists. Well, here's a really clever trick. Scientists can rearrange this equation a bit, so when they plot their experimental data on a graph, it forms a perfect straight line. And that straight line is like a treasure map for the reaction. I mean, look at what this graph tells us. The slope of that line, that literally reveals the reaction's activation energy. The spot where the line hits the y-axis, the y-intercept, that tells you about the orientation factor A. Once you have those two things, you can predict the reaction rate at any temperature you want. It's incredible. And that predictive power makes it an amazing problem-solving tool. You see, the equation has 5 variables in it. The beautiful thing is, as long as you know any 4 of them, like maybe you know the reaction speed at 2 different temperatures, you can always solve for the 5th one.
Now, for anyone who's actually going to use this equation, there are 2 huge pro tips that you cannot forget. First, temperature. It must always be in Kelvin. Not Celsius, not Fahrenheit, Kelvin. No exceptions. And second, you have to make sure your energy units for the activation energy and that gas constant R match. If one's in joules and the other's in kilojoules, you've got to convert. Those are the 2 most common places people mess up.
So when you take a step back, what have we got? We have this powerful equation that might look a little intimidating, but when you peel back the layers, it's just an elegant way of describing 2 really simple physical ideas: hitting each other the right way and hitting each other hard enough. That's it. That's the whole story.
So I'll leave you with this. Now that you know the rules, what reactions around you can you see in a totally new light? When you cook an egg, you're just adding heat to give those protein molecules enough energy to get over their activation barrier. When a car rusts, it's the exact same set of rules. It just has a much higher energy barrier, so it happens incredibly slowly. It's all the same molecular dance, just playing out at different speeds all around you.